All right, I wanted to run through a solution to this problem as everybody's filing into class because I'm not going to have time to go over it today. So we're going to begin by drawing a free body diagram of this block, and I'll choose red. So we've got a normal force pointing up, a weight pointing down. We have a tension force pulling it, and we have friction going to the left. Now the deal is, I don't know if the block's going to move or not, and that's what I'm going to use the static coefficient of friction to figure out. And just to kind of remind ourselves, we're pulling with a force of 9 newtons. So if our static friction, our maximum static friction is bigger than 9, we know the block doesn't move, because if the max static friction is bigger than 9, we need the max static friction amount to even get it moving in the first place. So here's what's going to happen is I'm going to go ahead and calculate this right now. So friction is going to be mu times n. And in the y direction, this is from the last unit, I know that normal balances the weight. I know it balances the weight because the block doesn't fly up into the air or fall into the ground and accelerate in any way like that. So I know that weight is mg, and so I'm going to have 6, and I'm going to round g to 10 here. And so I'm going to get 60 newtons. So I'm going to get friction. The max static friction is 0.3 from here times 60. And that's going to give me 18 newtons of force. Now, the force needed to push the block is 18 newtons to get it started. I'm only applying 9 newtons, so in this case, the block is not going to move. Now, for the next part of this problem, we know that the weight is 60 newtons. Let's take a look here. Again, free body diagram, we're going to have the normal, the weight, we have a pulling force, and we have the friction. Now, again, from the previous, we know that the weight from the previous, and so we also know that the static friction is 18 newtons from the previous page. That's the maximum static. And since we're applying a force of 60, we know that, yes, it moves. Since it is moving, I can now use the coefficient of kinetic friction. So yes, it moves. I can use the coefficient of kinetic friction to get the acceleration of the block. And here's how I'm going to do that. I have the pulling force to the right minus the friction to the left. And they no longer balance. They now make the mass accelerate. By the way, this equation is not something you're given on the exam. You're expected to be able to come up with this by looking at the free body diagram. So I'm going to have 60. Minus, now I need the coefficient, I need the kinetic friction, so that's going to be friction is fun, which is friction is 0.1 times my normal force of 60, so that's going to be 6 newtons. And the effect is we're going to make the 6 kilogram block accelerate, so that's going to be 6 times A. And when we solve for A, we're going to end up getting 9 meters per second squared. So part 3 is the only new part. So your job is to look at this free body diagram, study this equation, and before you leap and say, I don't know is not acceptable. Look at the free body diagram, look at this equation, look at the elevator lab, look at those 3 things, and try to figure out your best idea of how I came up with this equation from the free body diagram. And this idea that I have to combine forces, that's what this crazy symbol means, combine the forces to get MA when it's not balanced.